Hi there, Rachel Chase here, and in the next video in this series about hypothesis testing, we will explore testing claims about means where the population standard deviation is unknown. Now, once you have the general concept of hypothesis testing, there's really no difference other than essentially the table and the test statistic that you use. When sigma is unknown, if you recall from confidence intervals, we use t instead of z. So our test statistic, in other words, our t-test, is equal to almost the same thing that we learned about when sigma was known. It's our sample mean minus our population mean divided by this time the standard deviation over the square root of n. Let's take a look at an example. The McFarland Insurance Company Claims Department reports that the mean cost to process a claim is $60. An industry comparison shows this amount to be larger than most other insurance companies, so the company instituted cost-cutting measures. To evaluate the effect of these cost-cutting measures, the supervisor of the claims department selected a random sample of 26 claims processed last month. The sample information is given below. At the 0.01 significance level, is it reasonable to conclude that the mean cost to process a claim is now less than $60? So you'll see here they've given us a list of data, and the first thing you need to do with that data is go ahead and plug it into your lists and use one var stats to find out your mean and standard deviation. So for this problem, if it's already in one var stats, you can use your calculator as well for the data functions. If you're doing this by hand, just round those numbers to something reasonable. So let's say x bar is 56.42 since it's money, and your standard deviation take out to a couple more places if needed, maybe 10.0406 should be good. And for accuracy's sake, if you are concerned, you could take that further for your mean as well. Now that we have that information, what else have they told us here? We took a sample of 26 claims, and we want to know, has this been productive, essentially? Has the cost-cutting measures been effective in reducing the amount of money it costs us to process a claim? So if originally it would cost $60 to process a claim, and we found a mean of about $56, hopefully something did work out there. Now, think about what your null and alternative hypotheses are going to be. Also, we're testing this at the 1% significance level, so alpha is 0.01. The mean is our original claim of $60. The alternative is if the cost-cutting measures have worked, this number should now be less than $60. So we're back to a one-tailed test, and this time it's on the left side. So one-tailed on the left, that means alpha is 0.01 over here. So what do we do with all of this stuff? Well, the process is the same. Instead of finding a z critical, you're now going to find a t critical. If n is equal to 26, that means that we have n minus 1 degrees of freedom is 25. You can either use your table, in which case you'd find 25 degrees of freedom, and then across the top, look for the area in one tail is 0.01, and that gives us a t critical value of 2.485. Since this is on the left, it's going to be a negative 2.485. Another option you have to find that critical value is if you prefer to use your graphing calculator. Under your distribution, you see we have inverse t. Tell it the area to the left, in this case is 0.01, since it's on the left side, and how many degrees of freedom we have. In this case, we have 25 degrees of freedom. And obviously don't put that in a graph by accident. Try this again. So as you can see here, with rounding, we end up getting the same value. The calculator is just providing us the most accurate that it can. Whichever method works for you, you're welcome to use. Next up, find your t-test statistic. The test statistic is equal to the sample mean minus your population mean divided by your standard deviation over the square root of your sample size of 26. So go ahead and take a moment and type this in. And try that again without typos. So you can see here that when we plug in for our z-score, we get, our t-score, we get a negative 1.816. Which, same thing like with our z-test, if 0 is in the center, where does this fall? Falls right around here, which means it's not in our tail region, and therefore we have to fail to reject our null hypothesis. We do not have sufficient evidence which supports the claim. So if you're curious as to the sufficient evidence or not, anytime that you reject your null hypothesis, it means that you have sufficient evidence to reject that claim. When you fail to reject your null hypothesis, it means that you are lacking evidence. In other words, you do not have sufficient evidence to reject that claim of whatever it is you are testing. Let's take a look at the next one, and for this problem, we'll go ahead and use the t-test function in the calculator. The mean income per person in the U.S. is $40,000, and the distribution of income follows a normal distribution. A random sample of 10 residents in Wilmington, Delaware had a mean of $50,000, mean income that is, with a standard deviation of $10,000. At the 5% significance level, is there enough evidence to conclude that Wilmington residents have more income than the national average? So for starters, they told us that the national average is $40,000. We have a sample of n equals 10 residents with a mean of 50,000 and a standard deviation, so it's a sample standard deviation of $10,000. Let's test this at 5%. So if you sketch your picture real quick, can we conclude that Wilmington residents have more income? More is a directional statement, so that means that we are testing against our mean across the U.S. that Wilmington people have more income than the national average, so that's greater than 40,000. So that means that this is one-tailed on the right side. So this tail region is 0.05, that's what alpha is. And if you have n equals 10, then you have n minus 1, 9 degrees of freedom. So let's go ahead and find our t critical value here using the inverse t function. Now notice here, if this area is 0.05%, then everything to the left of it is 0.95%. So this way we don't have to worry about the positive or negative. It's 0.95 with 9 degrees of freedom. So that is a t critical score of 1.833. Again, feel free to use the table if you prefer. Next up, similar to how we use the z-test function, let's look at how you would use the t-test function for something like this. So let's tell it our population mean was $40,000. Our sample mean was $50,000 with a standard deviation of 10,000 and a sample of 10 people from Wilmington. We're testing this greater than. So according to this readout, if we have a t-test statistic, so that's this one right here, that's what you would normally plug into that big formula for, of 3.16, that fits way out in this tail region, since again, 0 is in the center. So in this case, we say that we reject our null hypothesis. In other words, we do have sufficient evidence that the mean income of Wilmingtonians is actually higher than the national average according to this. To round out this video before we learn about proportions, let's take a few minutes to talk about the p-value. P-value you've already kind of seen because of the computer readouts that we've looked at, but what the p-value does, and this is something that's very common in technology to use, is it gives you and it helps you make a decision based on the area as opposed to a test statistic or critical value. Basically, with the example of the previous problem here, since we already have it, we had an area in the tail of 0.05. So for example, if the test is one-tailed and this is 0.05, you compare the p-value to alpha instead of having to compare your test statistic to your critical value. A lot of this is personal preference, but they go hand in hand. It's just a different way of looking at it. Now, if you look at our readout here, we had a p-value of 0.006. So if our p-value was 0.006, and this area is 5%, this is less than 1%, that means that the p-value piece would be just right there. So just this last piece, whereas the alpha was the entire tail region. And you'll notice when this was our critical value and this was our test value, that's when the test value exceeded the critical value. So p-value is kind of cool in that context, and you will need technology to be able to find the p-value for a lot of these because you can only find p-value by hand when you're dealing with a z-test of some kind. So personally, I recommend become very comfortable with using these test functions. Even if you prefer doing the stuff by hand, at least it gives you a way to check your work over. So it's just really an option here. Now, if we go back to what we talked about earlier today in the previous video about our rejection decisions, how do you reject H0? If you're using the p-value method, p needs to be less than, so the p-value needs to be less than alpha. If, same thing. Now, when you fail to reject your null hypothesis, that means that the p-value is greater than alpha. So going back to this concept, 0.006 is in fact smaller than 0.05. This was our p-value, this was our alpha. When p-value is less than alpha, you reject the null hypothesis. Again, just another way of testing. So for the final examples in the next video, we'll look at proportion testing. We're going to use the p-value method exclusively just to see how this all fits in. Stay tuned for more.